Hi, thank you very much. I'm filling in for Professor Gerd Delarue, who, due to a small emergency, wasn't able to make it. And since we're tight on time, we'll just introduce this session of digital transformation and AI for climate change. Our first speaker is Marta Gonzalez, and her title is Multiscale Analysis for Improved Risk Assessment of Wildfires, facilitated by data and computation. Marta?
Hello, everyone. Thanks for the opportunity to be here to present my work. I'm going to be working in a very interdisciplinary, serious topic that is fire. For that, we team up from a team from operations research, city planning, and environmental planning. And we have Cristobal Pais, the main postdoc that work on this here in the room. And we have also Minho Kim, that is our PhD student. Let me start telling you some numbers about the challenge. Some of you that have property in the Bay Area may remember the 1991 fire at Oakland. In 4 days of fire in October, it cost what would be today $3 billion. It was 1991, $3 billion, and it burned out 1,500 acres. But fast forward to 2017, we had a 23 days fire that cost $1.3 billion, and it took 3 weeks to be burned out. It was the most destructive fire in California, 2017 in Santa Rosa. 3 years later, in 2020, we have the Paradise Fire that burned 153,000 acres, costing $16 billion. So the reason of this last fire was drought. So the region had received 40 times less water than what would be expected. Then drought with the Mont Diablo winds caused this amount of destruction. Then our goal entering into this topic is, first, we want to predict fire behavior. There are models that are called operational model of fire. We want to understand how the fire is spread, and we want to bring together the decision science for landscape mitigation strategy policies. That means 2 areas that are not usually combined, that are people working with environmental factors and fire modeling together with the people working with the mobility science. And we want also to introduce data and computation towards management evacuations. Then we have the planning aspect, the evacuation aspect, and this catastrophic fire modeling question. So the main opportunity we have is that we have data at an unprecedented scale. So the type of data that we are gathering, for example, are for the state of California, the entire road network with its 6 million segments. And we are covering all our 32 combined statistical areas in the state. Second data set that is very important to calibrate our models is the fire history. We have 100 years of fire in which we can know the ignition point, probable cause of the fire perimeter, and the area, what we call in fire the fire scars. That can be mixed with fire station, emergency facilities, and other aspects of this complex socio-technical problem. Then here comes the environmental factors that are important for us to gather. They are at 30 meter by 30 meter resolution. We need to have the digital elevation model, the slope, the aspect, and what would be the fuel component. That is all that has to do with the 13 classes of fuel vegetation. We have all digital in the same framework. And thanks to CAL FIRE, we have 3,150 fire stations all over the state. So thanks to data and computation, we have in our fingerprints the possibility to model all this. And let's start with the beginning, that is, okay, how are we going to do the prediction of the fire behavior and the intensity of a spread. That is the main dramatic risk component that we need to tackle. And in this arena, we have two types of models. One are the physical models that are in computational fluid dynamics that are very detailed, very high resolution, and we have the so-called semi-empirical models. The semi-empirical models are the ones that are computationally treatable for the large scale atmospheric type of modeling. And what they do is they use the Huygens equation. So basically you have a rule for fire propagation, and at every front of the wave you have an ellipse. And then you need to model at every time step, usually 1 hour, 30 minutes, how these ellipses are going to be transformed. And what we have, for example, is that when you see ABC are the dimensions of the ellipse, and the key parameter is R that I'm going to show in the next equation. The R is the surface fire spread rate. That is the fire spread rate is the main component we need to work with. And here are the Rothermel equations that basically what it have is in the left-hand side, we have most of the variables that have to do with the type of fuel. And we have this phi W and phi S that they have is the slope of the terrain and the wind. Those are the type of equation, and here we see example how at every cell you have the rate of a spread, and you have a cellular automata model that we have generated. There is a publication. It's called Cell to Fire that implement far side, that is the behavior of the fire is the state-of-the-art fire simulator. We just re-implemented it in a most parallelizable environment to have faster simulations. Then here is the challenge where we are at. What I'm showing in the left, in my right, that is your left-hand side, we have the fire in Paradise, and this is from the data. The red perimeter is the huge 5 scar was 150,000 square acres. And what we have is the days. So in blue and green are the first 3 days, from November 8th to November 11th. And the fire finished in November 20th. So here we have how the state-of-the-art simulators, here is the ignition point, and you have far side only model this blue area, and we need to model what is in the red and blue circles. Then our cell-to-fire modeler is giving us the orange area, is doing better than far side, but still, up to today, there is no operational fire modeler that is able to predict what's going on in these catastrophic events. And here is where we are working on how to generate models that do RL to better change the parameters such that we can improve this fire simulators model. That we are, this grant started 6 months ago. We are exactly at this point in how to better develop these type of models with, and notice that we have already the equations. What we are planning to do is mostly do data assimilation towards better forecasting of the wind and understanding the parameters of the ellipse development. So that is where we are at. And in the remaining time, I want to show you the second scale we're working on, and this is the decision side for landscape mitigation strategies and policies that have to do, once we know the risk factor in the different areas, what we tell to the planning agencies. For that, we create this risk index at the state level again, that basically is developed by adding together different factors. The fire behavior is a function that is normalized in the entire state, and it contains the rate of spread and the fire intensity. And notice that behind this rate of spread, it was the previous hard question we were developing. So fire behavior is one aspect in the state, and the other is the socio-demographic layer that contains amount of people and home values in the polygons. We do exabytes of 0.1 square kilometers in the entire state. And we have, for this exabyte, what is the shortest travel time from the fire stations. Then there you have it, your entire state, what is your risk according to the fire behavior, how many people, what is the value of the house there, and how far they are to the closest fire station. So with that, we put it in the computer, and what we are aiming to do is, what we are doing is a integer mix optimization problem in which we have the risk index that have the variables I already told you, and then we have ys, yi, the sum of yi are our fire stations, and xij is the presence of the centroid that need to be served by a fire station. And what we are minimizing is the risk index that contain the travel time and what we have in that grid I. Then to tell you an example of the results, we zoom in the LA County, and we noticed that while looking the travel time distribution of the fire stations to that centroid, immediately we see zones that are underserved by the current fire station. We have travel times of up to 50 minutes. So if the fire starts there, and then we can add the fire behavior in the same grids, and we have how here our risk index distribution that is built with the factors I told you before. And then what is nice here that in your risk index distribution we have important places where the people live and places also that due to being isolated with higher fire behavior, they are going to be in trouble. And here we have an example of the output of the optimization in which we have the current station's location and what would be the optimal station locations. Then what we can have is all the exabytes in purple, they would, with the new distribution of fire stations, they would not be affected. The ones in black, if you have an optimal distribution of fire station, they would do worse, but everything that is in yellow, this amount of pixels, is going to benefit in the optimal case. So, of course, we cannot relocate all our fire stations. What we are doing currently is an assessment of which are the regions that are less well planned. And of course, we can implement the optimization problem in which where to add, where are the places where we need to add. But at this moment, we're doing a risk assessment of how far from optimal is the planning of our stations in the state of California. Then I would like to enter into the summary. We need to develop physics-based models informed by MI to improve prediction of fire behavior. Data and decision science allow us to target vulnerable locations at the state level. Our next steps include managing evacuation and comparative risk assessment of the entire state to plan for new fire stations. And with that, I would like to open for questions. Thank you.
I think you mentioned it, but weather forecasting for a couple of days, even a couple of hours, seems to play a central role in planning efficient fire response. Did you say it is incorporated here?
Yes, exactly. That is where we would like, and particularly wind. That is what we want to include into these models, because the current simulators have usually of every 1 hour, and I think we can do much better than that, and that's the plan, exactly.
Because we have similar issues when we plan our wind farms, right? We want to know how that all works. Okay, thanks.
So in a similar vein, you said that wind played a big part, and then slope, I didn't realize played a big part.
Yes.
How does slope come into effect? Is it more slope is bad?
More slope accelerates the spread of fire. And then the other aspect in terms of that is longer term is drought. Yeah, that is much worse, getting worse and worse, and that is affecting and higher temperature, it also affects our. But for now, I think what it would be more impactful is doing AI, even with parameter-free models within the feasible parameters, and really check it and being able to generate these multi-day fires is surprising. It's such a relevant topic, and the current simulators can only simulate 3-4 days of fire. So I think this is a perfect opportunity that is what was funded here, injecting AI. Even if it's parameter-free, we can model the many days and then go back to the physics. But also incredible is the actual physics of fire is not what is being used because it cannot be managed. What is used is these semi-empirical models. We do not aim to go into much higher resolution. We're going to keep with the empirical models, both informed by AI and data simulation from weather forecasting. I do have what? The second part?
Videos of the fire as it burns.
Ah, that's wonderful. Yes, that is part of, there is a recent NSF report on this. Part of what is shaking the field is the UAV's videos. And in fact, the ending of the NSF report on this meeting on fire, they say, the question is not if we're going to be able to forecast fire, it's whether, it's when. So it's a fact, it's coming. And Europe is using Farsight, that is the benchmark modeler of the US, into their forecasting. So Europe started ahead.
But these videos are short-lived. They're only for short periods. You don't have a continuous video for the period that the fire burns.
Well, actually, they are. For example, the researchers that are more advanced on this is in Australia. They have longer videos. We in the US did not record the several days of fire we have had. However, why we need the videos is to train our models.
I think in the interest of time, we'll have to push the last question, sorry, to offline, just because we don't want to push Tom again. So let's thank Marta one more time, please.
Thank you.